Whenever you send a text or just turn on a light, there's this incredible hidden world at work. It's this beautiful symphony of billions of tiny parts all moving in perfect harmony. And believe it or not, the rules that run that entire show, they're actually way simpler than you think. So let's dive in and take a look. Just try to wrap your head around this for a second. We're talking about billions of components on a chip the size of your fingernail, all working together flawlessly. It's like trying to choreograph a dance for the entire population of a continent, but on a microscopic stage. It seems absolutely impossible, right? But it all boils down to just a few basic principles. And that's really the secret here. The magic of all our modern electronics isn't in some overwhelming complexity. It's actually in its incredible simplicity. So right now, we're going to pull back the curtain and look at the handful of rules that literally make our entire digital world possible. So where do we even begin with something so huge? Well, we start at the very, very beginning with the absolute foundation of everything, the electrical network, or, what we all just call a circuit. When you get right down to it, every single electronic device, I don't care if it's a simple toaster or a massive supercomputer, it's just a collection of these electrical elements, all hooked up together. So to understand how the whole thing works, we first have to meet the key players. All right, let's get to know this cast of characters, the building blocks of every circuit. The best way to do this is to group them into a few key categories, which really helps us understand the different jobs they all have. Okay, so first up, think of a circuit kind of like a tiny city. You've got your power plants. Those are the active elements. They're the ones generating all the energy and pumping it into the grid. Then you have all the homes and factories. Those are the passive elements. They're the ones that use up that energy or maybe store it for later. One side provides the juice, the other side puts it to work. Simple as that. Next, we can think about how the electricity actually moves through these parts. Some components, they're like a busy two-way street. The traffic, which is our electrical current, can flow freely in both directions, no problem. But others are strict one-way streets. They've basically got a giant do not enter sign for any current that tries to go against the flow. Now, here's where it starts to get really interesting. Some components are super predictable. Just look at the graph on the left. See that perfectly straight line? That tells us its behavior never ever changes. It's reliable. But then you have others, like the one on the right, well, they're a bit more like a winding country road. See that curve? Its properties actually change depending on the voltage or current. They're a little less predictable, but they let us do all sorts of cool stuff. So let's talk about the real engines of these circuits, the power sources. Without them, nothing's going anywhere. But, and this is a big but, there's a huge difference between how they work in the textbook and how they work in the real world. You see, in a perfect theoretical world, we have something called an ideal voltage source. It's this perfect little box that gives you a rock-solid, constant voltage no matter what you do or how much power you try to pull from it. And that graph right there, that perfectly flat, horizontal line, that's the dream. That represents a power source that just never quits, never sags, no matter how hard you push it. But I gotta ask, does that really exist? Well, here's the reality check. In the real world, every single power source, every battery, every power supply has a tiny bit of what we call internal resistance. You can think of it like a little bit of friction or a small speed bump that's just built in and you can't get rid of it. So what does this little speed bump do? Well, have you ever been in a car at night and noticed the headlights dim just for a second when you start the engine? That's it. That's internal resistance in action. And you can see it right here on this graph. That downward slope shows that the more current you pull, the more that voltage starts to drop. That's the real world for you. Okay, so we've met the players. Now it's time to learn the rules of the game. And in the entire world of electronics, it really just comes down to two fundamental laws that everything has to obey. We have a guy named Gustav Kirchhoff to thank for these. So Kirchhoff's first law is all about what happens at an intersection. Any point where two or more wires come together, we call that a node. Think of it like a junction in the road. And his current law, or KCL, is beautifully simple. Whatever amount of current flows into that junction has to be the exact same amount that flows out. You can't lose any of it, and you can't create any new current out of thin air. It's basically the law of conservation of traffic. What goes in must come out. Now, his second rule is about what happens when you take a complete trip around a circuit. Anytime you follow a path that starts and ends at the same point, we call that a closed loop, something very neat and predictable happens with the voltage. Okay, The best analogy for this is hiking. Imagine you start at the base of a mountain. You climb up, you gain a bunch of elevation. Then you come back down the other side, and you lose all that elevation. By the time you get back to your car, where you started, your net change in elevation is 0, right? That is exactly what Kirchhoff's voltage law says. All the voltage you gain from power sources and all the voltage you lose across components, it all has to add up to 0 once you get back to where you started.
All right, so now we've met the components and we know the two unbreakable rules of the road. So how do we actually use this stuff to figure out what's going on in a circuit that looks kind of complicated? Let's put these pieces together and solve the puzzle. So imagine you have a really messy circuit with a bunch of different power sources all pushing and pulling at the same time. How do you even start to analyze that? Well, you do what you do with any big problem. You break it down into smaller, simpler pieces. And in electronics, we have a really clever trick for this called the superposition theorem. The way it works is brilliant. You just focus on one power source at a time. You temporarily turn off all the others, calculate the effect of that one source, and then you repeat the process for every single source in the circuit. Turning off a voltage source just means replacing it with a wire. And turning off a current source means creating a gap in the circuit. Once you've figured out what each source does on its own, you just add all those effects together to get the final answer. And here's exactly what that looks like. In this picture, we want to see what that 3 milliamp current source is doing all by itself. So what do? We just take those two voltage sources and replace them with plain old wires, short circuits. And look at that. Suddenly the problem gets so much easier to solve. It's all about tackling one piece of the puzzle at a time. And really, that's the whole story. We started with a few basic components. We learned two fundamental laws that govern everything. And with just that, we unlocked a powerful method to analyze even really complex circuits. That journey, from just a few simple rules to our incredible modern reality, that's the story of electronics. When you stop and think about it, it's pretty amazing that these few, simple, elegant rules are the foundation for everything, from your coffee maker to the rockets we send into space. It's just a powerful reminder that sometimes the most incredible and complex things are built on the simplest ideas. It really makes you wonder, doesn't it? If these same few rules got us this far, what are they going to build next?